On October 7, 2025, the European Space Agency unveiled the initial official photo of 3I/Atlas, an interstellar visitor spotted gliding close to Mars. Everyone anticipated a major discovery. What emerged was a dim, blurry spot and 4 days of quiet from all prominent space organizations. Why did NASA, along with China and the UAE, withhold their superior shots while only ESA attempted to dismiss chemical signatures that defied logic? A path that seemed unnaturally precise and a surrounding glow almost entirely made of carbon dioxide. If 3I/Atlas turned out to be merely another comet, why did each explanation only spark further doubts? And what secrets do 7 probes hold from the public? Here's the narrative behind the photos that transformed our understanding. Just past 9 a.m. local Mars time on October 2, 2025, the Perseverance rover's Skycam captured a snapshot that seemed insignificant at first. Skycam serves as a broad-field color device designed to track dust storms, clouds, and the Martian skyline, not to pursue objects from beyond our solar system. Yet, as anticipation built for detailed orbital views, this modest lens sees the earliest distinct trace of 3I/Atlas approaching Mars. The unprocessed frame NASA shared afterward displayed a subtle green-ringed mark amid the faded red planet's atmosphere, so faint that it might have gone unnoticed without the added label. Detection faced steep challenges. Mars's daytime glare, amplified by airborne particles, renders distant celestial intruders nearly undetectable. The Skycam's detector, fine-tuned for scenic vistas, had difficulty extracting details past the most prominent elements. Still, Mallory Leafland, overseeing the rover's operations that shift, insisted on extending the camera's activity. She contended that even a basic recording might mark a milestone, particularly amid the U.S. government shutdown that risked halting non-critical missions. Her decision proved fruitful. The photo, logged at 0918 Mars local time, provided the inaugural concrete proof of 3I/Atlas entering the region around Mars. No surface tool on the red planet could scan the full heavens simultaneously, above all in broad daylight. While orbiting craft and research lenses awaited ideal positioning, Skycam's expansive perspective enabled it to snag the unforeseen. The outcome lacked polish, a rough blotch scarcely separable from static, but its presence was irrefutable. This lone shot, from an instrument intended for meteorological duties, laid the groundwork for the sequence of detections that ensued. The quest for clarity gained its origin, an authentic view from an alien world's ground depicting an interstellar guest in Mars's airspace. October 3, 2025, witnessed an uncommon gathering overhead on Mars. 7 distinct spacecraft, each excelling in its niche, aligned to scrutinize 3I/Atlas as it skimmed within 30 million kilometers of the surface. Far from an ordinary pass, this event united detectors for a one-time shot at an outsider from deep space. HiRISE, the high-resolution imager on Mars Reconnaissance Orbiter, excels at rendering Martian terrain with clarity to discern rover paths. However, its limited scope demanded pinpoint accuracy to nab a shifting comet so far off. CASIS aboard the ExoMars Trace Gas Orbiter provided greater adaptability. Its black-and-white system could layer images, sacrificing definition for better detection of elusive, wandering subjects. Themis on Odyssey, focused on infrared bands, sought a heat outline, though prospects were slim. Typically, its sensors overlook comets without active ejections of vapor or particles. Mars Express supplied 2 analyzers, Omega and Spicum, crafted to chart ground minerals and air components. They shone in breaking down the coma's makeup, hunting for signatures of carbon dioxide, water vapor, or anomalies. Nomad, another analyzer on the Trace Gas Orbiter, aimed to uncover the subtlest hints of unstable substances, possibly revealing the object's extraterrestrial roots. China's Tianwen, 1 orbiter contributed varied spectral and radar capabilities, distinctive for examining makeup and form when conditions allowed. The UAE's HOPE mission, orbiting at greater heights around Mars, offered ultraviolet and visible light surveillance attuned to shifts in the coma's luminosity and contours. Every tool confronted unique barriers. intensity thousands of folds dimmer than standard subjects, pursuing and traversing the heavens in brief observation periods. Nevertheless, for a short span, Mars emerged as the solar system's prime observation post. The complete suite of gear, from crisp visuals to chemical scanners, prepared for an unrepeatable trove of information. In that brief interval, the potential shone brightly. Should any oddity or insight appear, this was when the global fleet of satellites and landers would seize it. ESA's announcement hit the public on October 7th. Rather than a crisp depiction, viewers received a cycling video, a vague, indistinct point wandering over a dark backdrop, encircled by a scarcely visible mist. This came from the Cassis instrument in action. Scientists working on the ExoMars Trace Gas Orbiter directed their instruments toward the anticipated trajectory of Comet 3/Atlas as it approached Mars. The difficulty proved overwhelming. As Nick Thomas, lead investigator for the Cassis instrument, explained, the comet appeared at least 10,000 times fainter than the usual Martian objects his group monitors. In order to prevent signal interference, Thomas restricted each exposure to just 5 seconds. This cautious approach favored reliable data over eye-catching images. The final animated sequence condenses many hours of work into mere moments of movement, where every frame records an object barely discernible. Rather than revealing the comet's core, which stayed indistinct even from this range, the visuals depict its coma, a faint shroud of gas and dust extending thousands of kilometers. The glow of the coma diminishes swiftly, blending into the ambient interference without any sign of a tail. ESA's release noted uncertainty in the spectroscopic evaluation, essential for determining makeup. The unprocessed files and initial data products stay secured behind the organization's routine 6-month restriction. Just this refined teaser is available, standing in for more thorough examinations still in progress. Public engagement standards require some display, yet much of what Cassis observed remains concealed. ESA's media team advocated for bolder visuals, but Thomas held his ground. No enhancements, no exaggerated contrasts. The danger of misleading viewers was significant, particularly amid whispers of odd compositions and potential irregularities. At present, this restrained video offers the sole authorized peek. It serves as a humble yet crucial document of an extraterrestrial guest near Mars. Researchers must bide their time, aware that true insights lie within datasets not due for release for months. On October 4, 2025, key figures from NASA, the European Space Agency, China's CNSA, and the United Arab Emirates convened a private video meeting. Absent from any open schedules and without a leaked record, the discussion's effects were swift. Over the ensuing 3 days, all Mars-focused organizations fell quiet. ESA alone shared output, one reserved video clip and a vague written update, avoiding details. NASA blamed the continuing U.S. government shutdown for sparse reports, though that didn't affect their European or Asian counterparts. Neither China nor the UAE, navigating their own governmental dynamics, provided any rationale. Within ESA, the strain was evident. PR personnel sought a sensational unveiling to fulfill eager audiences anticipating a landmark cosmic rendezvous. However, safety experts and research heads resisted, employing terms typically linked to asteroid defense scenarios, odd initial findings, risks of confusion, and requirements for cross-agency scrutiny. References to media hype eroding confidence cropped up in several internal documents. In the aftermath, preliminary announcements underwent repeated revisions, swapping out descriptions of peculiar reactions or baffling light patterns for neutral promises of continued review. The hush extended beyond mere omissions. While ESA applied its standard 6-month hold to raw Cassis materials, even basic overviews of light scattering and spectral details were pared down severely. Teams from NASA's Mars Reconnaissance Orbiter and Perseverance rover issued nothing past the labeled SkyCam image, funneling inquiries to central offices. China's Tianwen-1 mission and the UAE's Hope orbiter, both outfitted for distinct optical and scanning observations, refrained from announcements, not even verifying observation attempts. The normal flow of scientific releases, preliminary views, and technical notes halted abruptly. Experts in space governance recognize the unusual alignment. Rival organizations seldom synchronize their reticence, particularly around prominent breakthroughs. The prior instance resembled this occurred amid asteroid close approaches with defense concerns, where premature info might spark alarm or misunderstanding. Yet this involved a comet, posing no hazard. Thus, what sort of oddity could compel for entities with divergent goals and competitions to withhold all but the most guarded teaser? Speculation ranged from chances of misinterpreting subtle readings or igniting theories of artificial sources to underlying disputes on validating and explaining early signs of atypical elements or unforeseen light behaviors. This unified restraint stranded the research field in uncertainty. Engagement groups handled inquiries without responses. Hobbyists attempted and couldn't replicate the Skycam sighting, intensifying gossip that the true narrative lurks in restricted archives. For the moment, the sole assurance is that an element in the early results, be it a measurement glitch, a natural peculiarity, or just concerns over a potential media frenzy, had prompted leading global space organizations to hold back. The push for transparent research had run up against a barrier of prudence, with the findings held pending a final assessment. The odds were stacked against 3I/Atlas from the start. Its route, deviating only 5 degrees from the ecliptic plane and weaving past Mars in October and Jupiter's path in March, challenged all expectations. Experts at ESA's Space Situational Awareness Division crunched the figures, determining that a stray interstellar visitor tracing this precise layout occurs less than once in 10,000 cases. That course by itself sparked intrigue, particularly since the flyby zone edged near the spot of the 1977 WOW signal. Internal reports brushed off the alignment as mere chance, yet the slim probabilities ignited discussions among the project's researchers. Analysts examining light spectra confronted an odder enigma. Initial readings compared from the VLT and JWST revealed prominent nickel atomic features without any iron signals. Typically in comets, these metals emerge in tandem, freed from dust particles by solar heating or UV radiation. In this instance, iron stayed absent even as nickel output spiked with every solar approach. By August 21st, the VLT measured nickel release at roughly 10 to the 22.7 atoms per second, following a scaling pattern so sharp, declining with distance from the Sun to the power of F, that it surpassed all documented comet patterns. Simulations in labs suggest a single mechanism: nickel carbonyl, a fragile molecule that arises in CO-rich settings and decomposes easily under gentle warmth or sunlight, yielding isolated nickel atoms. On our planet, it's a standard manufacturing technique. Out in the void, it's virtually unprecedented. Without signs of iron carbonyl or any iron emissions, specialists at DLR and INAF hunted for organic interpretations matching the observations. The surrounding envelope, probed by JWST in the near-IR, revealed another layer. CO2 comprised 95% of the gases identified, an unusually high proportion seldom seen. H2O, the mainstay in typical comets, appeared in negligible amounts. Certain experts suggested prolonged cosmic travel might evaporate water ice, concentrating denser compounds. Alternative views speculated the imbalance could signal intentional design, like exhaust or fuel systems, although nothing concrete backed such notions. At present, the CO2 heavy envelope served as a distinctive chemical marker, uncommon yet feasible in natural formations. Visual observations introduced one more surprise. Data from KSSGS and VLT's FS2 captured unusually deep negative polarization, reaching -4% or greater in red light, well outside the norm for comet particles. Such negativity indicates the envelope's grains redirect light toward intense backscattering, commonly tied to tiny carbon-laden bits or metal aggregates. Among inner solar system comets, dips seldom go under -2%. These results nearly doubled that extreme, holding steady over various tools and viewing angles. Instrument glitches couldn't account for it. Checks with reference stars and fresh trials confirmed the readings. Collectively, the observations sketched an exceptional scenario. A hyperbola laced with improbable planetary encounters, a composition ruled by nickel and CO2, and light-scattering traits straining established theories. Individually, each irregularity might pass as a quirky rarity or chance outlier. Yet as the details accumulated, justifying a unified everyday rationale became increasingly untenable. The sealed archives, unprocessed spectra, polarization metrics, and operational records formed the heart of an astronomical conundrum calling for unconventional insights. Currently, all theories must grapple with these deviations: the orbit, the makeup, and the optics. Researchers confronted a mystery requiring a solid basis. 4 rival frameworks vie for credibility, each offering a distinct route to resolution. The initial, most restrained approach views 3I/Atlas as a standard comet boasting unusual reactions. Should this hold, upcoming scans ought to echo the nickel surplus and CO2 abundance, while uncovering concealed iron or water traces as the envelope shifts. The next theory posits it as a relic device, maybe a scout or monitor inactive for eons. This aligns with the factory-style nickel processes, though no hints of form or engineered transmissions have appeared. Just advanced radar imaging or irregular rotation might sway the balance. The third envisions a functioning surveillance unit, fine-tuning its route for close planetary passes. The alignment matches, but no traces of control signals, venting adjustments, or power signatures exist. Spotting abrupt velocity or luminosity shifts post-perihelion would prove decisive. The final, boldest concept describes a composite vessel masking a crafted interior within an organic facade. Such a setup could justify the organic surface alongside the quirky reactions. Still, no proof of unnatural actions has emerged. Solely trajectory shifts after perihelion or debris displaying unnatural movement might ultimately verify the hypothesis. Every hypothesis depends on forthcoming evidence for validation. Currently, the observations are straightforward, though the conclusions remain elusive. On October 29, 2025, as 3/Atlas reaches its nearest point to the Sun, visibility across the inner solar system vanishes. Observers on Earth and Mars lose sight of the body as it slips behind the Sun's disk, obscured by intense plasma and blinding light that defeats both optical and radio detectors. Over a 2-week span, the perihelion zone becomes an observational void, omitting the pivotal stage from all scopes and missions. This observational gap extends beyond mere logistical hurdles. It forms a cosmic veil precisely when activity peaks, increasing chances for comets to flare up, break apart, or, should the entity prove artificial, perform some adjustment. Project coordinators can only bide their time, aware that abrupt shifts in path or emerging debris will escape detection. Priorities upon reappearance are straightforward: monitor the trajectory, hunt for anomalies, assess the coma's luminosity, and probe for unforeseen satellites. Events hidden in the solar glare could determine which explanation endures. Yet for the moment, information flow ceases, forcing all resolutions to hinge on the object's re-entry into viewable skies. In late November, the initial chance arises to spot 3/Atlas post-solar occultation. ESA's JUICE probe, en route away from Jupiter, will direct its advanced Janus imager and Magus spectrometer along the anticipated route. The alignment is precise, less than a degree from Jupiter's position, yet the spacecraft is ideally placed to image the coma provided it retains sufficient illumination. JUICE's observations won't transmit immediately. Preliminary visuals may delay by 3 days, while comprehensive datasets could require up to 2 weeks for processing, validation, and archiving in planetary science repositories. Juno, tracing its prolonged polar trajectory, will attempt its observation in mid-March 2026. By March 16th, optimal positioning enables JunoCam to detect venting plumes or pieces that could indicate artificial influences. The timeframe is limited, and data dissemination lags. Photos might not become public for a month or longer. Each mission group is developing backup strategies should 3I/Atlas deviate from predictions or fade abruptly. Meanwhile, global audiences hold their breath as these remote observers calibrate their instruments, eager to witness the unfolding drama that has already transformed protocols for studying celestial travelers. Even with 7 probes oriented for viewing and Perseverance's prior aerial recording, NASA, China, and the UA have withheld their visuals and analyses. This unified reticence, noted in an intra-agency discussion on October 4th, deviates from norms in collaborative astronomical efforts. Released information shows an orbit with under 0.1% likelihood of natural formation, a spectrum dominated solely by nickel, and a surrounding envelope of 95% carbon dioxide. Diverging from all documented comets, specialists concur that 32/Atlas's essence stays unresolved, with vital examinations postponed beyond the October 29 perihelion obscurity. As ESA and partners gear up for upcoming disclosures and JUICE's November flyby, a key truth emerges. This interstellar passage, the most notable since Oumuamua, has sparked far more inquiries than resolutions. Upcoming visuals could redefine our understanding of extraterrestrial intruders in the solar system.